Welcome. In this explainer, we're cracking open the expert's playbook for two classic coding interview problems. These are the kinds of questions that really trip up so many developers and can make or break your chances at a top tech company.
Okay, let's dive right in. Take a good look at these. These aren't just some abstract puzzles, you know? They're basically gatekeepers, designed to test not just what you know, but how you think. So, the real question is, how do you beat them? Well, let's find out. First, let's set the stage a little. Picture this. You're in the interview, the whiteboard is staring back at you, and the interviewer lobs a question your way. It's specifically designed to see how you think about data, how you can manipulate it, and really how elegantly you can solve a pretty tricky problem all while under pressure.
All right, let's move on to our first big challenge, untangling what's called a multi-level linked list. Now, I know when you first see it, it can look like a complete and utter mess of tangled pointers. But the solution, as you're about to see, is actually, well, it's pretty elegant.
So here's the core of the problem. You get a linked list, but there's a catch. Some of the nodes don't just point to the next one in line. They also have a child pointer that kind of branches off to a whole separate list. Our job? We have to merge all of these child lists back into the main one to create a single, perfectly flat structure.
So this shows us exactly what we're starting with. We've got a simple main list, right? 1 points to 2, 2 points to 3. Easy. But look closer at node 2. It has that tricky child pointer that veers off to this totally different list starting with 7 and 8. That right there, that's the knot we need to unravel.
And boom, this is our goal. This is what done looks like. Notice how that child list, the 7 and 8, has been just seamlessly spliced in right after node 2. And this is crucial. The rest of the original list, starting with node 3, is now perfectly tacked on to the very end. It's all one beautiful continuous chain. So, how do we actually do that?
Well, it really boils down to a methodical 4-step process. First, you just walk through the main list until you hit a node that has a child. Simple enough. Second, you go down that child list and find its very last node, its tail. Step 3. This is where the magic happens. You perform a kind of pointer surgery to splice that child list in. You can think of it like cutting a film reel and sticking a new scene in the middle. You've got to connect both ends perfectly. And finally, you just clean up after yourself by setting that original child pointer to null.
All right, you ready for the big one? This is a true interview classic that shows up all over the place. We're going to build the perfect cache, specifically an LRU cache.
The idea itself is pretty straightforward. An LRU cache has a fixed size. When it gets full and you want to add something new, you have to kick an old item out. And the rule is simple. The item that's been sitting there the longest without being touched, the least recently used one, is the one that gets the boot. The real challenge, though, isn't what it does, but how fast it has to do it.
And when I say fast, I mean instantly. We need what's called constant time performance, that's O of 1, for both getting an item and for adding a new one. This means the operations have to take the exact same amount of time whether the cache has 10 items or 10 million. I mean, how is that even possible? Well, the secret is this brilliant combination, this power couple of data structures that work together in perfect harmony, a hash map and a doubly linked list. The hash map is our super fast lookup specialist. It gives us that instant O of 1 access to any item just by its key. And the doubly linked list, that's our timekeeper. It lets us reorder items in O of 1 time, which is absolutely essential for keeping track of who's the least recently used.
I love this analogy. Think of it like a VIP line at a club. Every single time an item is accessed, whether you get it or put it, it gets to jump to the very front of the line, the head of our list. This automatically marks it as the most recently used. So what happens when the club is full and a new person shows up? Simple. We just kick out the person at the very, very back of the line, the tail of our list, because, by definition, they are the least recently used.
Okay, let's zoom out for a second, because this is probably the most important lesson here. Solving these problems is not about memorizing code. No way. It's about recognizing the underlying reusable patterns that are the building blocks for countless different solutions. These patterns right here, things like fast and slow pointers, using a dummy node, or that hash map and doubly linked list combo we just mastered, this is your real toolkit. This is your secret weapon. Recognizing when to pull out one of these fundamental patterns is the key to solving problems you've never even seen before.
In this table, this is basically your strategic cheat sheet. The problem description itself often gives you all the clues you need. If you hear words like cycle or find the middle, your brain should immediately start screaming fast and slow pointers.
If you're wrestling with annoying edge cases at the beginning of a linked list, a dummy node can save you a world of pain. And if you hear that demand for O of 1 lookup and O of 1 reordering, you know it's time to call in our power couple.
So we've walked through the logic, we've identified the core patterns that make these solutions tick. But here's the thing about all this. Just understanding it is only the first step. It's not the step that actually gets you the job.
And that brings us to this quote, which is honestly the most important takeaway from this whole thing. Theory is great, but implementation is everything. So my challenge to you is simple. Close this explainer, open up your favorite code editor, and build both of these from scratch. No looking. That is how you truly get ready.